which is stress concentration and notch sensitivity. Okay, so like we had a stress concentration for static loads, we can define a stress concentration for fatigue loads, and I'll define that next. Fatigue load stress concentration. So if you recollect, stress concentration for static load was the stress without the change in geometry to the stress where the geometry was regular. Similarly, we can write fatigue load stress concentration as the fatigue strength of, in this case, the discontinuity is due to a notch, the notch-free specimen. I might have reversed the. Let me just quickly check this. I think I might have reversed the expression. It's notch free, yeah. Or to the fatigue strength of notched. Okay, so we know that the stress concentration, for example, factor is greater than 1. And in this case, Kf is also greater than 1 because, or greater than or equal to 1, because the fatigue strength of a notch-free specimen is always going to be greater than the fatigue strength of a notch specimen, because adding notches decreases the ability of a material to withstand stresses. So that factor will probably become will be greater than equal to 1. Yeah, so what we can do is we can define the maximum stress as Kf times sigma 0, just like we defined it for static loading. And similarly, we can define a similar factor for shear stress, and I'll call that Kfs tau 0. So sigma max, tau max are maximum, normal, and shear fatigue stresses, and sigma 0, tau 0 are just the normal or the nominal, whatever you would like to call them, shear fatigue So this will be for the notch free, and this will be for the notched specimen. So clearly notch free would have a higher strength than notch free. So there's another factor which we need to define, which is totally new. It's called notch sensitivity. Okay, and this takes into account the fatigue and the static stress concentration due to fatigue loads and due to fatigue loads as well as the static loads. So it's defined as Kf minus 1 divided by KT minus 1. And there's a similar one for shear. It's KFS minus 1 divided by KTS minus 1, where KF, we've defined this, I'll just not define that again. So KT and KTS are stress concentration factors for static loads in normal stress and shear stress modes. What's going on? Okay, so if you get Q equals 0, so when will Q be equal to 0? It will be when KF equals 1, which is saying that if you look at the definition, it says that the fatigue strength of notch-free specimen equals the fatigue strength of notch specimen, right? So that's when KF equals 1. We say that the specimen has no sensitivity. In other words, the presence of the notch doesn't really affect the stress. If Q equals 1, then KF will be KT, and we say that the specimen has full notch sensitivity. So what is of interest to us is figuring out these stresses, finding the maximum stresses, right? And how do you go about doing that for fatigue loading? And so the procedure is as follows. So I'm going to give you how we do this. So first of all, so let me write. So the section is how to compute KF and KFS. Okay, step 1 is compute KT and KTS from the geometry. Okay, so this is something we've covered in chapter 5, section on stress concentration. So once you define the geometry, you can refer to the right table in the appendix, and that gives you the stress concentration factor, KT, based just purely on the geometry. It is not a function of the material. Once you get that, then compute Q or QS from the figure shown below. And I'll put the figure in a bit. Okay, so that's the next step. And then once you have Q or QS, you can compute KT and KTS using the following formulas. Okay, so I'm just going to take that formula we wrote down earlier and just move things around. So it's not a new formula, it just comes from the definition of notch sensitivity. KF equals 1 plus Q KT minus 1, and then KFS equals 1 plus QS KTS minus 1. Previous page, they're not new. Okay, so I'm going to show you the figures you need to compute Q and QS. They are basically empirical values. So here is, there are two figures which you need to know depending on the means of loading. Okay, let's see this render mistake there. Oh God. Okay, let me see if I made an error there. Yeah, it should be. Thanks for checking. It's KF and KFS. You know, let me see how I can put these figures, embed these figures from the book. Insert picture. Okay. No, it's not going to work. Okay, that's figure one. And then I need to put another one. So let's go to the next page.
Is that figure what's in the book?
Yeah, it's in the book. And if you go to this section 610, you should see it. Okay, so let me light a little bit on that figure. So what you need to note is there are two figures, right? What those figures are for. So this one is for the notch sensitivity for reverse bending or axial loads, okay? So keep that in mind when you look at this figure. It basically gives you Q as a function of notch radius, which is basically specified in the problem, right? And then you can find the appropriate curve based on the ultimate strength. So this ultimate strength in IPS, ultimate strength in SI units. And so you look at the right curve and then find the notch sensitivity based on ultimate strength, the notch radius, and the material, which is here. So the next one is the notch sensitivity in reverse torsion. Okay, so what you need to do again is the same thing, which is figure out the ultimate strength, figure out the notch radius, and figure out the material. So SUT, 2 is R, and 3 is material. Once you have these three things, you can find what is the value for Q, and that will go in step 2, and that you can use to find K. Okay, now that's one way of doing it, which is there is this plot. You could also try to express the relation between Q, which is this, and R as an equation. So you look at these curves and you try to use some regression tool to fit the equation. So another way to Q fit a relation between Q and R using the above figures. Okay, and if you do that, the expression actually is not terribly complicated. It is just something like this: 1 divided by 1 plus square root of A divided by square root of R. Okay, you know what? Let me just number them. That will be useful when I do the problems. Let me call this as 1, the equations in the algorithm, and then let me call this as 2. Okay, we'll be using this in when we solve problems. Okay, so here we can see that R is clearly the notch radius. What is A? Well, it turns out that square root of A is a constant called the Newberg constant, and that is something which is clearly dependent on the material. So if you look at these curves, it depends on SUTR and the material, right? But R is taken care of in that equation. We only are left with 1 and 3. So we need to find the A, which should probably depend on 1 and 3, which is the material, right? The strength and if it's steel or aluminum. So what they do is we basically give you a formula which tells you what this A is, square root of A is. And you just use that formula to find square root of A and use that for problems. So this is what it is. So square root of A is experimentally determined. It can also be found from the curve fit, but for steel, one is in bending and axial loading. Let's go in the background. 0.246. It's a really long expression. So minus 0.246 minus 3.08 10 raised to negative 3 times SUT plus 1.51 10 raised to negative 5 SUT square minus 2.67 10 raised to negative 7, oh, sorry, negative 8 SUT cube. Okay. It's fairly long. And this is true for SUT is in the range 50 and 250 kpsi. Okay, so when you have steel, you don't normally go above 250 kpsi. That's why that's the limit, and that's in the IPS unit. So if you want to do it in SI units, then it is 1.24 minus 2.25 10 raised to negative 3 SUT plus 1.6 10 raised to negative 6 SUT square minus 4.11 10 raised to negative 10 SUT cube. Okay, and this is when SUT is in the range of 340 and 1400 MPa, 1700 MPa. Okay, so in IPS units, which is the top formula, you want to use SUT in kpsi, and square root of A is in inch raised to half. In SI, SUT is in MPA, and square root of A is in raised to half. Okay, so we're not done yet. So we need to still do torsion. Okay, that's for steel in bending or axial loading. So here is torsion. Okay. Again, long expressions. Square root of A is 0.19 minus 2.51 10 raised to negative 3 times SUT plus 1.35 10 raised to negative 5 SUT square minus 2.67 10 raised to negative 8 SUT cube, and that's when SUT is between 50 and 220 kpsi. There's another formula for SI, and that's 0.958 minus 1.83 10 raised to negative 3 SUT plus 1.43 10 raised to negative 5 SUT square minus 4.11 10 raised to negative 8 SUT cube, and that's when SUT is in the range 340 and 1500 MPa. Again, the same units are true. You want to use kpsi for IPS for SUT and MPa for SUT and SI, and then the units of square root of A will be either in inch or raised to half, depending on the units. So let's call this just puts few numbers here on the equations which we'll be using. Let's do let's call this set. Let's see. Let's call it 3A. Is it bending and axial loading? Okay. Let's call this 3B. Let's move to the next page. A lot of space here. What's that?
I think it's annoying when you copy paste stuff because it makes it really annoying to keep up with written paper.
Oh, okay. Yeah, these formulas are all in the book. It's not that they are from a different source. Okay. Okay, so what we can do is there's some simplification we can do, that is take equation 2. Okay, so you can take equation 2, which is a function between Q and R, and then take equation 1, which is this one, and sort of eliminate Q, because Q is, we don't really care about Q, right? We only care about KT and KFS. So I'm going to write another expression down, and this will be the final one before we start solving problems. So to make life easy, we can simplify, substitute 1 or 2 in 1 rather, to eliminate Q. So we get the following expression: Kf equals 1 plus Kt minus 1 divided by 1 plus square root of A divided by square root of R. And that's going to be my final expression for this section. Let's call this, I think, 4. Okay, so we did a lot of things here about concentration factor. Let's see how they are actually used to solve and solve problems. Okay, so next is problems. Yeah. So, okay. Okay, a steel shaft has an ultimate strength of 690 MPa. So SUT is 690 MPa. And a shoulder with a fillet of radius 3 mm connecting a 32 mm diameter with a 38 mm diameter. Estimate Kf using the figure. Okay, so the figure was that figure which I showed you, that's for the notch, right? Q versus R, and then equations. So the equations which we used were, I think, in this case, that recollect, it was equation 2 and 4. So those equations related the notch sensitivity to the radius through Newberg's constant. So it will be Q as a function of A and R, right? Those. So we're just trying to see if we get the same answer if you use the figure versus using that formula. That's the point. And then there's something else which is kind of important here is how do you estimate KT? Because remember, in algorithm, we need to first estimate KT. I can actually copy paste that section, and then it's easier to follow that methodology to solve it. So let me take this. Copy here. Okay, so this is asking us to estimate KF using these two. So basically, this is also telling us how to estimate KF, right? The difference being that you have to use the figure, which is number 2, or the equation, which I have not written down here, but the equation is the second way of doing it. So that's going to be equation number 4 in the notes behind. So it's equation 4 is that one right there. Okay, so we got to essentially follow this. Now, before we start doing this, step 2 and step 3 are essentially using the formula. But what about step 1? We need to find KT and KTS from geometry. For that, we need to see something which we did in the past in chapter 5. That is the stress concentration depending just on the geometry. So we need to sort of understand what this question really means in terms of geometry. So it says that there's a shoulder with a fillet of radius 3 mm connecting a 32 mm diameter with a 38 mm diameter. So my inclination is there's a shaft of 32 mm diameter. There's another shaft of 38 mm diameter. And they are connected by some kind of a fillet. So like this. And so this is 38. This is 32. And this radius is 3 mm. So when you have something like this and it's stressed in this case, it's stressed in, oh, it's not given that. Okay, I think I used these, so I'm trying to find the loading condition here. It's not given there. So I assumed it to be bending and axial loading. So that will be given to you. Assume, let's say bending load. Okay, because that's important. Without that, you cannot find square root of A and also use that table. So it's basically bent, right? And then if you keep stressing it, it will fail. And for a material with a fillet, it's going to fail at that point where there's a fillet. That's where the stress concentration will happen. So what our first goal is to compute KT and KTS. In this case, it's not KTS, it's only KT because it's going to fail in normal stress and not in shear stress. So let's find, go to step 1. Find KT, but we need to figure out what that KT is based on the geometry. And so what I did was I went to the appendix and pulled up the corresponding figure. So I'm going to just dump it here. It's this one. You've probably seen it in the previous chapter. So this is a shaft with shoulder fillet in bending. Okay, and you need to, well, there's a moment M, but you need to find D and capital D and small d. And we know that capital D in this case is 38 mm, small d is 32 mm, and then the radius of the fillet, you know, is 3 mm. So I need to use these 3 pieces of information in order to figure out what KT is. So let's find capital D divided by small d, that's 38 divided by 32. So 1.1875. And then let's find what is radius r to d, and that is 3 divided by 32, that's 0.09375. So what I'm trying to do now is figure out what KT is. So I need to look at capital D divided by small d of 1.1875. So we have 1.1, we have 1.5. We don't quite have 1.18, which is 1.2. So we're going to go assume that this curve is approximately what we want to follow. And then we need to find R divided by D of 0.09, which is about 0.1. So 0.1 is here. This is going to be R. So we need to basically read off this. That's our KT. Okay, so this is probably half of, it's 1.6, right? This point, because it's midway between 1.1 and 1.4. So I'm guessing that this is 1.55 maybe. It's hard to say. So what I did was, and I just took the one to the book. The book says 1.65. And I think what they did was they assumed that since it's 1.18, they assume that this line is slightly above the 1.1 line. And so it falls just above 1.6. So they took it to be here somewhere. It's really hard to, so it's okay if you are in the ballpark of 1.6. So what I get is, so from the book, they say that KT is 1.65, but anything in the range of, I would say, in this ballpark is fine. So 1.5 to 1.7, if you assume any value, it will be right, because you just cannot quite pinpoint it from the figure, right? Okay, so this is, I'm going to take this book, this formula, this value from the book, but this, all these values are correct. Okay. Okay, so that's step two. Step one. Step two is to find Q from figure. Okay, so what's Q? Well, we have to go back to that diagram. So if you go here, okay, so this is for reverse bending or axial loading, and that's what we want. This is in bending, so we need to find the Q for a notch radius of, in this case, R is 3 mm, right? So 3 mm is, this is in mm, this is in inches, so it's 3. And we need the ultimate strength, and I think it's 690 MPa. 690 MPa. And this values seem to be in gigapascals. So what is 690 MPa? It's about 0.69 gigapascal, right? Or you need to multiply it by 1e-3. And so that seems to be very close to 0.7. Okay, so what we need to do is look at this curve and look at 0.3 and see where they intersect. So that's where they intersect. That's our point of interest. I would say, yeah, maybe 0.85. It's what I wrote. Yeah, you're very close. The book says 0.84, but 85, absolutely right. Anything in the range of, let's say 0.8 to 0.9 you take, you should be fine. I'm just going to take the book value and proceed. Okay, so Q is 0.84. Q equals 0.84. And the third step is, let's use the formula now. Kf equals 1 plus Q KT minus 1. 1 plus Q is 0.84. KT is 1.65. We found out earlier. And so this is Kf. Kf equals 1.55. And that's the answer. Okay, so we only, well, so this is the solution for part one, where we are trying to find Q from figure, right? We can also, as the question asks us, it asks us to solve this using a figure, using the equations, right? So only thing we need to do now is change this from using the figure to changing it to use the formula. So what I'll do is, let me just start it all over again. So part two. So first step, same as before, nothing changes. 1.65. Step two, this is where things will change, because you're not using the figure, but you're going to use the formula. And the formula is, use formula 4. The formula 4 is Kf equals 1 plus Kt minus 1 divided by 1 plus square root of A square root of R. Okay, so we need to figure out what square root of A is, because R is, we know it's 3 mm. Okay, and kt is 1.65. So let's figure out what square root of a is. For that, we need to go and figure out, go to the right table, right formula sheet. So this is the formula for A. So this is for bending and axial loads, and there's one for torsion. And since this is a bending and axial load problem, we need to use one of these two formulas. However, we are given the ultimate strength in MPa, which means that we need to stick to the SI formula. So we'll use this formula, the second one, because it's in SI. Okay, so I'm just going to copy that, sub in the value for SUT, which should be in MPa. So it's, I think, 690 MPa, and proceed from there. So square root of A is 1.24 minus 2.25 10 raised to negative 3. SUT is 690 plus 1.6 10 raised to negative 3. 690 square minus 4.11 10 raised to negative 10. $690 cube. And so solving for square root of A, we get 0.3142 mm raised to half. And since R is 3, we have Kf equals 1 plus 1.65 minus 1 plus 0.3142 divided by square root of 3. Okay, so by the way, I actually combined 2 and 3. So this is 2 and 3, because that formula 4 combines, just eliminates q, so you don't really have to solve for q. So solving it using this formula, Kf comes out to be 1.55, which is exactly the same as we found from same as 1, right? We get the same answer, which is what you let's start. So we were what we were doing, we were talking about stress concentration notch sensitivity, this factor Kf, and I outlined an algorithm to compute that. You need to find, it's right here, I think, page, yeah, find the Kt, which is something we covered in chapter 5, stress concentration. So we find that from the geometry and looking at the tables from the appendix. By the way, I posted all the appendix on Blackboard. It is, I think, is it homework? I think the homework tab, if you go scroll all the way up, you should see all the appendix. I just plucked everything, so you can use that henceforth for your needs for computing any values. Once we get Kt and Kts, we need to compute the notch sensitivity Q, and then once we do that, finding Kf is just a matter of using those formulas labeled as 1. Okay, and we solved one problem where there was this shaft with a notch, and we saw how to use the algorithm to solve that. Now here is another problem, which is in the same vein, but this time we have a physical system, and it's a little bit more intricate. It ties up concepts we learned before in chapter 5, and before that too, chapter 3. So let's read the question. So figure 6.22a shows a rotating shaft simply supported in ball bearings at A and D. So A is here, D is there, and rotated by a non-rotating force F, which is here, 6.8 kilonewtons. Using ASTM minimum strengths, estimate the life of the part. Okay, life of the part means we should be thinking of N, right? Assume the critical point is B. Okay, so they've done a step further. It also gives you the bending moment diagram, right? The bending moment is 0 at A and D because clearly there's no moment at the supports. And then it reaches a maximum at the point where the force is applied. Now the question is, if you want to compute N, we can think of this formula, right? where clearly if you know A, if you can compute A, let's say that we computed A, we computed B, then we can find N, provided we know S, right? What is S? S is the strength. So that the strength is the strength which will actually come from that figure, from that particular problem, right? We want to find at what point is the most critical part of that specimen. And when we talk about strength, we are, in this case, the loads are predominantly normal stresses due to moment. So we look at the normal stress. Okay, so N max will come from this diagram, clearly. So then we have a few candidates for the maximum stress. We have M max, MB, MC. Okay. Now you would think that M max will give you sigma max, right? It turns out that that's not true. It turns out that MB is the point where you have maximum stress. And the only reason the stress is maximum is because at B, where MB acts, there's actually a discontinuity, right? That leads to a stress concentration, and that stress concentration leads to a stress at B, which is greater than stress at the point of application for M max. We should just put sigma here. So if you were to do this problem as an engineer, you would probably, you actually find the stresses at different points and then find the maximum one. So it'd be a lot of computation. Just to save time, what I did was, I did this problem, I figured out what the point of maximum stress is, and I've identified that as B, which is, by the way, a step by computing the stress at different points. And we are only going to solve for the stress or assume that a critical point is B because some of the calculation has been done. But this is not normally what you'll get if you are analyzing a part. You need to figure out the point of maximum stress. Okay, so that MB will be used to find sigma, and then we can solve for N. Okay, so two parts. One is the things we've done in chapter 3, compute S, which is equal to sigma, using figure 622. And then some parts is chapter 6, which we're doing right now, where we'll compute A and B, right? This in this formula. And then finally, we'll combine the two and solve for N. Okay, so let's proceed. Let's just do this part first. It seems like the most straightforward part, A and B, since it's fresh in our minds. Okay, so what's A? A is A and B are the factors, and I'm going to write the formulas, and then we can ask ourselves what are the things we need in order to find A and B. So A is, if I'm not mistaken, it is F SUT square divided by SC, and B is 1/3 log to the base 10 the ratio of SC to FSUT. Okay, I think SUT is given. Let's go back. SUT is 690, and actually that comes from this ASTM minimum strength table. This is an appendix in the book, okay, but I just put the value here, 690 MPa. So we know that. Okay, let's compute the rest. F is actually kind of simple. There's a formula in the book that F is 1.06 minus 4.1 10 raised to -4 SUT plus 1.5 10 raised to -7 SUT square That's a formula from the book. I'm going to highlight that with blue just so that you can go back and check it. So then, yeah.
Is it F given the column?
F is not given. Sometimes it's given, sometimes it's not.
Is it 6.8 kilonewtons?
6.8 kilonewtons. No, that's, yeah, sorry. This is capital F. This is the force.
Oh.
Yeah, so capital F is given. That's the force. Yeah, my bad. It's small. We want small f, which is a part of the fatigue formula. 1.06 minus 4.1, 10 raised to negative 4. SUT is 690 plus 1.5, 10 raised to negative 7, 690 square. And F is, in this case, comes out to be 0.8485. We can just round it to 0.85. So F is sometimes given to you, small f. It's somewhere between 0.8 and 0.9. Otherwise, you need to use that formula to compute, which will be given to you. Okay, so we got F. We still need to find SE. Right? We need to find SE. Yes, for SE, there's a little bit of more elaborate work to be done. SE is KA, KB, KC, KD, KE, KF, SE prime. And those factors are something which we pull out from the tables, right? So what is SE prime? The formula for SE prime in SI units is 0.5 SUT if SUT is in the range, sorry, SUT is less than 1400 MPa, and it is simply 700 MPa if SUT is greater than 1400 MPa. So this is a formula which,
So the total should be 0.5 MPa.
what's that?
So like you have the 0.5 SUT and then below was 700 MPa. One of those three.
That's right. So it should be 700. So SUT in this case is assumed to be an MPa. So in this case, you'll see that you have to use the first formula. That SUT is 690. So SC prime is, so 690 is less than 1400. So 0.5 times 690, that is 345. Okay, now let's compute the factors, Ka all the way through F. Okay, Ka is the surface factor, I believe. And so let's go, and that depends on the kind of finish. And we need to check what the finish is. Is there any clue of the finish? Not really. I think that it says cold drawn in the caption. Okay. Okay, cold drawn circuit. Good catch. This is what we're looking for. Compute Ka. So we go back to the table, which I think I wrote down last time. I can, not this one. So this is a previous lecture. Let's go. Okay, so this is cold drawn. So we need to use, and we have SUT is an MPa. So we need to use A equals 3.04, B equals minus 0.217, and this is the equation. So let's use that. .14, 690 minus 0.21. This is Voltron. Okay, next let's find KB. KB is the size factor. Okay, and we need to figure out if this is a round specimen or not. So if this is a round specimen, so it's a rotating shaft. That's the key thing for KB. Let me mark that. And it's a round specimen. So we need to find what is the value for KB for a rotating round specimen. So let's go back to this. So we have rotating round specimen. The other thing which I forgot is what type of loading is this? It's not clearly not axial. It's actually bending load. So we need to go with these two. These formulas. The top one is in inches. The bottom one is in mm. In this case, since the problem is set in SI units, so we need to go with the second one. So let's plug that. Okay, and then paste it here. So you have a reference. And this comes from SI unit. First thing, it's a rotating round specimen. Okay, so the diameter in this problem is, I think, 3 mm. 3 mm radius, which means it's a 6 mm diameter. Sorry, my bad. That's for the fillets. It's 32 mm for the smaller section, 38 for the long one. In this case, you have to use the smaller of the two radii in the problem, because the part which fails is normally the shaft with the smaller diameter. So use the smaller of the two values. So 32 is what we'll use in this formula. So KB is, so it's 32, so it's, you have to use the first one. So 1.24, 32 minus 0.107 equals 0.86. Okay, so what are the other effects? Well, there is temperature effects. There is no temperature. This experiment is in room temperature, so we don't worry about it. So that's KD. KC is, I'm blanking on KC. Let's see what KC is. KC is to do with that's the temperature. So there's no temperature effect, so we can ignore KD. So it's 1. It's the loading factor. Yeah, so loading factor in this case, since it's bending, KC is simply 1. There's no temperature effects, so KD is 1. The reliability, we've not told anything about reliability, so we'll just take equal to 1. And then there's no miscellaneous factor. So KC is 1 and the remaining all are 1. So KC is 1 because it's a bending experiment. So let's put those values. K C equals 1 because of bending. KE, KD, KE, KF, all 1. Okay, so we can now find SE. It's going to be the product of all the Ks. So the first one we found was 0.74. Second part was 0.86 kb.
AA was 0.714.
Then I did a mistake. My notes have. Yeah, I wrote it incorrectly. 7.4, my bad. 7.4. 7.486, and then A rest is 1.1.1.1 times SE prime, which is we found is 345, and so SE is 220 MPa. Okay, so we got F, SE, and now we can find A and B. So A is F SUT square divided by SE square. So F is 0.85. UT is 690 given to us. Square of this divided by SE, which is 220. This comes out to be 1564 MPa. And then B is 1/3 log the base 10 of SE, which is 220, just computed, divided by F, which we also computed, 0.85, times SUT, which is 690. Okay, that is minus 0.1419. So to say, in this formula, we have now computed A and B. S is something which is unknown. So we will find N, but we'll have to solve for SF. Okay, this depends on the specifics of the problem. This problem, there is a specimen loaded in is a simply supported beam loaded by a force, right? So if we look at that figure, I'm going to redraw this figure with a force of 6.8 kilonewtons at a distance of 250 plus 75. That's 325 from the left, and then 225 from the right. Let's just draw a free body diagram first, and then we'll find the value for this moment B. So there's a free body diagram. Of the system, but I'm just drawing a beam because that's doesn't change anything. Since A and B are the points, I'm going to call them BA and BB. The force is slightly to the right, not exactly in the middle. The distance of the force from the left side is 325 in mm. And from the right, it's 225 mm. Okay, now there's a exercise we need to do to find what the reactions are. So we're trying to find the moment at B, right? B is at a distance of 0.25. It's sort of closer to so that I did D. Yeah, I should call this D. So that's the point D, and then B is somewhere here. That distance is 250. Okay, so now the first step is to find the forces VA and VD. So if you sum the forces in X equals 0, you have VA plus Vd minus 6.8 times 10 raised to 3 equals 0. And then if you take moments about any point you would like, let's say equals 0. Okay, I want you to fill the dots, right? This is something which you've done in the past. So after solving for A and D, VA and VD, you get VA equals 2.78 kilonewtons and VD equals 4.02 kilonewtons. So if you sum it up, you'll see that it's equal to 6.8. Okay, so now we've got that. Let's do the bending moment diagram. Okay, so we don't need to draw the bending moment diagram. It's already given to us. We only need to find the moment at B. So what we do is we draw the section of the beam till B. We apply VA, which is now given as is something we found, 2.78 10 raised to 3. And then there's a moment, which is an unknown. And its distance is 0.25. Okay, so that's all we need to find MB. So 2.78 times 10 raised to 3 times 0.25. This moment is about B, and it acts in the clockwise direction, right? This way. So we have a negative sign. And then we have MB acts counterclockwise. So we have MB as positive equals 0. And solving for MP gives us 695 Newton meter. So we've got the moment. Let's get the stress. So the stress equation is stress is My divided by I. So the y is the distance from the neutral axis, right? This is y. In this case, y is d divided by 2. And I is the inertia. It is pi d raised to 4 divided by 64. And so sigma is m divided by pi 32 m in the numerator and pi times dq. So m is 695 pi. D, as I said, the smaller the diameter, the bigger is the stress, because as you can see that D is inversely proportional to sigma. So we have a choice between 32 and 38, 32 being the smaller. Since we're interested in stress here, we have the smaller diameter, bigger diameter. We want to go for the smaller one because stress is higher. So we sub in 32 mm in meters is 0.032 cube. Okay, so this comes out to be 216 MPa. It's a really long problem. Okay, so we found the stress, but the thing is, remember that this is a shaft, and we're trying to find the stress here. Because there's a notch, the stress here is going to be higher than 216 because we need to include the effect of stress concentration. So now what we need to do is we need to find Kf. And once we have Kf, we can multiply with sigma, and that will be the true stress at B. So sigma max will be Kf times sigma, which we just found. And the way to find kf is kt from table to q from table, and then kf is 1 plus q. What is the formula? It's 1 plus q kt minus 1. Okay, so that's what we need to do. Fortunately, it turns out that I'd given you the same geometry in the previous problem. So if you look at the previous problem, Q1, we had the same one. We had 38 mm diameter, 32 mm, 3 mm fillet. So that saves us some time. We can just take the value we got for KF from the previous problem and just plug it in. But if not, then you need to go through this whole procedure, which we did for Q1, to find the right value for KF. Okay, so KF will take us 1.55, but it's quite a few steps. So let's put that in. So we KF for we computed KF for this geometry in the previous problem, and we found KF is 1.55. So we'll just use that. So sigma max is 1.55 times sigma, and sigma is 216. So sigma max is 335.9 MPa. Okay, so finally sig SF, which is the stress, which is the place where this thing is going to break in fatigue failure, is going to be B. And so the stress there is SF, which will be sigma max, just found, is 335.9 MPa. Okay, the final step is use SF equals A n raised to B. You need to find n. It is SF divided by A divided by B. SF is 335.9. A was 1564. B was negative 0.1419. Okay, that gives me n equals 5.1 to 10 raised to 4, which you can also write as 51 times 10 raised to 3 cycles. Okay,